In this video, we'll discuss series that cannot be evaluated using the properties that we discussed in the last video. However, they are really easy to evaluate. These series are called telescoping. Let's start with the definition. A telescoping series is a series whose partial sums only have a finite number of terms after cancellation. And the word that you want to focus on in that definition is the word cancellation. What makes a telescoping series unique is it doesn't have nearly as many terms as you think it does, but you have to take a closer look to figure it out. Let's see an example. In this example, we're asked to determine a sum that cannot be evaluated based off of the methods we've learned so far because we have a k in the denominator. No worries, this will be an easy sum to evaluate if you just take the time to plug in a few terms and take a closer look at what's happening. When we plug in k equals 1, we'll get the expression 1 over 1 minus 1 over 2. And then since this is a series, we should add. When I plug in k equals 2, I'll get 1 over 2 minus 1 over 3. That's when you plug in k equals 2. When you plug in k equals 3, you'll get 1 over 3 minus 1 over 4. We could continue in this manner, and we should, all the way until our upper limit of k equals 100, in which case we'll get 1 over 100 minus 1 over 101. At this point, I can look and see that this series is not quite as scary as it looked at first. Rather than simplifying 1 minus 1/2, what I notice is that the negative 1/2 in this part cancels with the positive 1/2 in this part. And that's also true of the negative 1/3 and the positive 1/3. Negative 1/4 and a positive 1/4, that would be in the next k equals 4 term. Likewise, the term that comes before this last one would be 1 over 99 minus 1 over 100. So this term will cancel. The only terms that will remain is the initial 1 over 1 and the final minus 1 over 101. And thus, to evaluate this sum, I just have to subtract 101 from 1, which is 100 over 101. And that's how a telescoping series works. At this point, you can see why the telescoping series got their name. In a sense, you're able to see right from the beginning of the series all the way to the end, just cutting out all of the middle. Another image that I like to have in my head is one of these collapsible telescopes that look like this, where you can imagine the telescope all stretched out or nice and compact. In this example, we're presented with a very complex looking series that doesn't appear at first glance to be telescoping. That is, I don't see any cancellation from one term to the next. However, if you take this series and write it in sigma notation, you might notice something interesting. Give this a try. Pause the video and rewrite this series in sigma notation with a lower limit of 1. Here's what I came up with. Remember that sigma notation is not unique, but if we use a lower limit of 1, I think we would both agree that the series that is being summed should look like 1 over the square root of k plus the square root of k plus 1. That describes the structure of every single term in the series. And I should use an upper limit of 24, so that the last term that gets plugged in is 1 over root 24 plus root 24 plus 1, or 25. Okay, so why is this a telescoping series? Well, here's an idea. We have square roots in the denominator. If we were to get those square roots out of the denominator, we would do so using a conjugate. The conjugate would be the square root of k minus the square root of k plus 1. And the standard practice is to multiply our fraction by the square root of k minus square root of k plus 1 over itself. What that does is gives us a new way to look at our sum. Our sum now becomes the sum from 1 to 24 of root k minus root k plus 1 over, and think about what happens when you multiply out this pair of binomials down here. Your first term would give you just a k. Your outer and inner terms would cancel, and the last term will give you minus the quantity k plus 1. Now, of course, when we subtract k minus the quantity k plus 1, we get negative 1. And so that means we can rewrite this series as the sum from k equals 1 to 24. From dividing by a negative 1, I can just switch the minus sign to root k plus 1 minus root k. Aha! This looks like a telescoping series to me, and I can see that by writing out a few terms. Let me show you what I mean. When I plug in 1, I get root 1 plus 1, or 2, minus root 1. Plus, when I plug in 2, I get root 2 plus 1 minus root 2. When I plug in 3, I get root 4 minus root 3, and so on, until I get to the last term, and I plug in root 24 plus 1, which is root 25, minus root 24. And now I can see the cancellation. As I go through and cancel my terms, I see the root 2's cancel, and the root 3's cancel, and the root 4 will cancel, and even the minus root 24 will cancel with the term that came before it. And thus, I'm left with nothing other than the square root of 25 minus the square root of 1, which of course is equal to 5 minus 1, or 4. Here's another example of a series that's telescopic, but it doesn't appear to be at first glance. Here's a cool strategy that you can use to figure out this series. I'm going to think about this series as a sequence of partial sums. The first term in my sequence will simply be the first term in the sum, 1/2. The second term in my sequence will be the sum of the first two terms, 1/2 plus 1/6. The next term in my sequence will be the sum of the first three terms, 1/2 plus 1/6 plus 1/12. Where's this all headed? Look at the fourth term. It'll be 1/2 plus 1/6 plus 1/12 plus 1/20. Okay, so what? It'll keep going like this. What do these fractions simplify to? Take a second and simplify the additions. The first term's 1/2. The second term, 1/2 plus 1/6. What do you get? What about when you add a 12, a 20th? Pause the video and simplify the next three terms in the series, or the sequence of partial sums, and see if you get my drift. When I add the first two terms in the series, 1/2 plus 1/6, I get 2/3. When I add the first three terms in the series, 1/2 plus 1/6 plus 1/12, I get 3/4. When I add the first four terms, I get 4/5. Do you see the pattern now? If not, I'll tell you. When I add the first 5 terms, I get 5/6. And when I add the first 6 terms, I get 6/7. This continues. So the question of what is this sum really just boils down to how many things am I adding together? And since I'm adding the first 10 terms in this series, I'm going to get 10/11. Now that might be a very clever solution. However, it doesn't really explain why this series is telescoping. In order to explain that, I'm going to rewrite this series in sigma notation. And I'm actually going to do it in two different ways. The first way will be thinking of this series according to this pattern. 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4, and so on, all the way up to 1 over 10 times 11. When I put that into sigma notation, I see it's the sum from k equals 1 to 10 of 1 over k times k plus 1. Now when I look at that series, I see that it represents the series I was asked to evaluate, but it doesn't appear to be telescoping. I don't see any subtraction. I wouldn't expect any terms to cancel out. But let's look at another way to express this sum in sigma notation. This time, I'm going to rewrite a half, the very first term in the sum, as 1 minus a half, because they're equivalent. The second term, 1/6, I'll write it as a half minus a third. Those are, of course, equivalent. The third term, a 12th, I'll write it as a third minus 1/4. Again, equivalent. The last term in the sum is 110, and that's the same as 1/10 minus 1/11. This isn't at all obvious when you look at the sum for the first time, but it does bring up an important point of recognizing a telescoping sum. When can we recognize the telescoping sum, and when is it too challenging, and maybe you need a little extra algebra? Well, when I write out the structure that I've created here, it'll always look like 1 over k minus 1 over k plus 1. Okay, k and k plus 1 are always going to be right next to each other, and that implies to me that there's going to be some cancellation. We can see the cancellation in this expanded form, but we couldn't see it in the other expanded form. If you're able to get your series into a form that looks like this, where you have a k and a k plus 1, or maybe a k and a k minus 1 consecutive terms, you have a good chance that you'll be able to evaluate that sum using sigma notation. This brings up an interesting idea. If this entire sum that we worked out here is nothing more than 10 out of 11 when we added the first 10 terms, what would happen if we kept going? Well, in sigma notation, we have a nice way of saying, just keep going. That's putting the upper limit as infinity. Here we're looking at the infinite sum of a series 1 over k times k plus 1. In the last example, I showed that this should be equivalent to the infinite series from k equals 1 to infinity of 1 over k minus 1 over k plus 1. That structurally, this fraction and the difference between these two fractions will be the same for every single term. Okay, let's try to use the idea of a telescoping series to see what the answer would be. When I plug in 1, I get 1 minus 1/2. When I plug in 2, I get 1/2 minus 1/3. I'm supposed to keep going like this. But when do I stop? Well, since the upper limit is infinity, I never stop, not for any term, ever. And so, in the end, the half cancels out, the third cancels out, the fourth cancels out. Actually, everything after this 1 here in the beginning will cancel out. And therefore, this infinite sum adds to 1. There's a lot of interesting things that you can do with telescoping sums. It's important to keep the big idea in mind, and that's that not every single sum can be evaluated using the properties and the formulas that we came up with in the last video. Sometimes it requires looking at a greater depth, and other times it's as simple as plugging in a few terms and seeing if anything cancels out so that you can evaluate it much more efficiently. Thanks for watching.